Good afternoon.
Good afternoon, everyone.
Good afternoon, sir, madam, everybody. So, okay, sir. Good afternoon, Ghosh sir, namaskar.
Good afternoon, namaskar. Good afternoon.
Madam, Pina madam, namaskar.
Namaskar ji.
Yeah. So, we can report here. Are you ready from Cochin?
Yes, sir.
Can I just try sharing my screen? I just wanted to make sure that it works.
Okay, you can have a just testing, but I think there will be no problem. You are physically visible means there will be no problem. But still you can have.
Yeah. Thank
Yes,
you.
sir. Okay, sir. Good that Tyagi sir has joined.
Very good afternoon and welcome to this first technical session. So, let me compliment QSET and INTROMET Society for chalking out very elaborate program, 3 parallel sessions going on. So, we start. Patnaik.
Welcome to the
Yes,
day
sir. Just can we check who are the present or not so that accordingly we will arrange the time.
Is the time will start at 2:05.
Yeah. Just
Okay, let
check.
me start. Welcome to the day 1 technical session TS1B of INTROMET 2021 on climate variability and extreme weather events. In this session, we have 2 lead talks by Dr. Subimal Ghosh and Dr. Veena Balan Sarojini. The first lead talk will be delivered by Dr. Subimal Ghosh, Institute Chair Professor, Department of Civil Engineering and Convener, Interdisciplinary Program in Climate Studies, Indian Institute of Technology, Bombay. We welcome you, sir, to this session.
Thank you. Sure.
It's a great pleasure to have Dr. Veena Balan Sarojini, scientist, Research Department, Earth System Predictability Section, European Center for Medium Range Weather Focus, UK, to deliver the second lead talk. We welcome you, ma'am. The lead talks are followed by one invited talk by Dr. Ramesh Kumar Yadav, Scientist E, Indian Institute of Tropical Meteorology, Pune. We welcome you, sir. After the lead and invited talks, we have 6 short oral presentations. We welcome all the presenters to share your contributions in this session. This session is chaired by 2 distinguished personalities, Dr. Ajit Tyagi and Dr. D.R. Patnaik. Dr. Ajit Tyagi is the retired Director General of Meteorology at IMD, New Delhi, and is the former President of Indian Meteorological Society. Dr. Tyagi has served as Assistant Chief of Air Staff Meteorology and holds immense research and teaching experience with specialization in numerical weather prediction and aviation meteorological services. Sir, we are honored to have you to chair this session. Dr. D.R. Patnaik is the head of Extended Range Prediction and Numerical Weather Prediction Group at IMD New Delhi and is the President of Indian Meteorological Society at present. His research interests include monsoon and climate variability, climate prediction, extreme weathers, and extended range prediction. It's a privilege to have your presence to chair this session. We welcome you, sir. The lead talk is for 20 minutes plus 5-minute discussion. Invited talk is for 30 minutes presentation plus 2-minute discussion, and short oral presentation is for 9 minutes plus 1-minute discussion. We request the speakers to adhere to the time allotted. The selected questions in the chat box will be read to the chairs by the rapporteurs. Now, may I request the honorable chairs to kindly take over the session.
Thank you so much, and you have done spade work for us by outlining the program and giving the timelines to the esteemed speakers. Well, this is a very important topic because the thrust of climate change challenges and includes the impact part of the extreme weather events, and that how the climate variability and climate change is posing a challenge to all of us. So we have, as already mentioned, eminent speakers. The session covers wide-ranging topics, extreme weather events, modeling, prediction. So I'm sure it will be a very, very interesting as well as educative. session for young researchers and also for policymakers and administrators. I request Dr. Patnaik to take care of the timings, because this is very important. We have got long sessions with number of speakers, so everybody should get due timings as allotted. So may I request all speakers to stick to the timings so that we can have question answer sessions also. Dr. Patnaik could give some warning signals at the right stage if it's overshooting. Thank you so much. I really enjoy it, and thank organizers for giving me this opportunity and honor to chair this session. Please go ahead.
So just takes 1 minute. So all the lead and invited are there. I'd like to know whether other speakers are there. Ajil Kotayal, is there? Arun Kumar?
I'm there, sir. I am there.
Okay, Arun Kumar?
Yes, I am here.
Ranjit Kumar?
Yes, sir. Good afternoon. I'm here.
There. Jayanti Pal? Dr. Jayanti Pal, Central University of Rajasthan. Dr. Nageshwar Rao is there. Murali. Hello, Murali, I have seen you. Probably one speaker is not yet reported. Dr. Jayanti Pal. Okay, so we will just check in between. So that time, because we have to use that time also with some other.
Okay, sir.
Yeah. So I think, sir, already we have introduced, and the session reporter also introduced. So now may we invite our Dr. Subimal Ghosh to kindly give his talk on extreme rainfall and floods in a changing climate. Over to you, sir.
Thank you so much, Dr. Patnaik. And thanks to the organizers for inviting me. I'm really honored and humbled to be invited in this very important workshop. And I'll be talking about extreme rainfall and floods in a changing climate, and also in what way we can improve the forecast and some of our experiences. Dr. Patnaik, would you mind, just alerting me at around 17 minutes or so that we can.
Okay, sure, sir.
Thank you so much, Dr. Patnaik. So rather than going for a detailed introduction of extreme precipitation, this is kind of known theory that as per the Clausius-Clapeyron theory, it is expected that the water vapor capacity of atmosphere increases by 7.5% per degree warming. And this increase is actually reflected in extreme precipitation. Now, if you look into our very recent AR6, so this is, I was a lead author in chapter 11, and chapter 11 prepared this kind of a very nice figure where you can see where it has been shown that the regions where there has been increase in extreme precipitation. If you look into this figure, it looks very like the map, and the increasing regions are shown with green, the decreasing are yellow. Of course, there is no decreasing region. And also it also shows that how much confidence do you have that this increase can be attributed to human contribution. So of course the increase is quite with a very high confidence we can say that there has been an increase over the South Asian region, but we have limited evidence because of limited number of literature to say that these are because of the anthropogenic activities. So whatever be the reason, but the most important part is that the extreme precipitation has been increased over the South Asian region. Now why this extreme precipitation is a very difficult task, and this was a very nice fact which has been designed by IPCC AR6, which again came from chapter 11, where it was shown that why extreme precipitation are very difficult to project and predict. So it's a very simple example. If you look into the mean change in temperature and extreme change in temperature, you can see that the directions are almost similar. You may not see a very different pattern in the spatial pattern of changes in mean temperature and extreme temperature. But if you look into, this is the mean precipitation change and this is the extreme precipitation change, you'll find a lot of dissimilarities, because precipitation is a very difficult variable to simulate, simply because there is a lot of spatiotemporal variability. There are different factors, the instabilities happen at a different resolution, etc. And it's very difficult to really simulate them with coarse resolution model. And because of which, if you consider the, I mean, even if you see the projections, you'll see a very different kind of things, and that makes an extreme precipitation are really difficult to predict because they are not having the similar kind of sign up as the mean precipitation in terms of changes. Now, considering this fact, now how to really understand that whether the extreme precipitation, whatever is increasing, is it really following the Clausius-Clapeyron scaling or not? If not, why they are not following? So these are certain questions which are there, and there are a lot of research which are actually going on. And if you really need to estimate the scaling means the increase of precipitation extremes per degree centigrade of warming. There are different methods. And there are two methods which are quite well discussed in the literature. The first method is known as binning technique. So binning technique is sort of like this. So let's say if you have the PT, precipitation temperature, or stream flow temperature, if you want to do a stream flow scaling, precipitation temperature pairs or stream flow temperature pairs, you can consider, and you divide the temperature into different bins. That means, let's say 22 to 23 degrees centigrade one bin, 23 to 24 degrees centigrade one bin. This is the way you divide it into different bins, and you find out the you just plot the precipitation temperature scatter plots there, and find out in each bin what is the average value of precipitation. And you know that differences among the bin, let's say one is 22 to 23 degrees centigrade, one is 23 to 24 degrees centigrade. You know the differences, and you also get a change in the precipitation mean, and in that way you will get the scaling. So this is known as binning technique. The second technique which is used is known as quantile regression kind of technique. So quantile regression is sort of like this. It estimates. So normally if you perform a regression, what this tells us that given a regression or regressor, what is the mean value of regressant? But when you're doing a quantile regression, it tells us given a regressor, what is the extremes value of regression? What is the 99 quantile value of regression? What is the 95 percentile values of regression? In the same way, what we do, if you consider temperature to be the regressor, let's say, and let's say precipitation is the regressant, then what will happen? Given a specific temperature, what is the 99 quantile of temperature precipitation? What is the 95 quantile of precipitation? And you can find out from the slope of that quantile line will give you the binning value. So I'm giving an example of quantile regression. Let's say if you have the salary and the expenditure, if you have something, and then the expenditure of a person does not really directly depend on salary. Like for the same amount of salary, people may have different expenditure. There are people who actually spends a lot. There are people who doesn't spend a lot. So in that way, you need to get the quantile. So in the same way, for a temperature, for a specific temperature, the mean precipitation reacts in a different way, the extreme precipitation reacts in a different way. And the quantile regression helps us to understand that how the extreme precipitation really reacts with the warming. Now, if you look into the the data which are available over the South Asian region, we wanted to check for both stream flow and precipitation. And if you're considering the common portal which is available, the GRTC, the runoff data portal, of course, India doesn't have much representation. So we have to consider these are the regions over the South Asian region. This was published very recently in GRL. So this is region 1, this is region 2, and region 3. And we tried to plot the scaling, extreme precipitation scaling. So these are essentially the extreme precipitation value. And if you look into the scaling, you'll find that over the extratropical region, little bit of subtropical to extratropical region, there you'll get the scaling is positive actually, 5 to 7%, which is as expected. But if you look into over these regions, you'll find that scaling rates are actually kind of negative. And this negative scaling rates can be because of multiple factors, because these are humid regions. There are a lot of dynamic factors that affects extreme precipitation and so on. So they can be defined. But the most important point which I'd like to mention is that, but if you look into the daily stream flow to temperature sensitivity or scaling, everywhere except 1 or 2 points, everywhere the temperature has actually increased. The stream flow has actually increased with warming temperatures. So everywhere you can see a very high positive scaling, which is there for stream flow, but which is not there for precipitation. So the first question is that why precipitation has sort of a negative scaling over the tropical region. And the second one is why stream flow has exactly opposite kind of scaling over this region. So these are the major two science questions which we are trying to address. The first question we address partially, and what we are finding is that if you are considering the tropical region, the temperature is very high. So your moisture demand is quite high. Sometimes most of these demands are not easily met, and because of which probably there is a negative scaling. The second one is can be dynamic factors, and the third one also what we have found is that the cloud radiative factors also affect the scaling. So these are the certain regions because of which the precipitation temperature sensitivity may be different. Maybe with dew point temperature you may get a better result. But the thing what is more important is that stream flow and precipitation has a different kind of opposite kind of scaling, and this needs to be explored further. So what we try to do is that we try to check daily precipitation and 3-hourly precipitation scaling. So we have used the TRMM data to understand the daily and 3-hourly. First, we compared the Aphrodite and TRMM for daily precipitation. We are finding that yes, around 22 to 23 degrees centigrade, if you consider, there is a drop down. So the scaling curve drops down after 22 or 23 degrees centigrade. There is a cutoff temperature. And this is consistent among Aphrodite and the TRMM dataset. But if you go ahead with TRMM dataset for 3-hourly, then you will find that this drop down is not necessarily happening, which is very consistent with the stream flow. So what is being observed is that 3-hourly precipitation has a sort of a positive scaling. You can see that for region 3 there is a very much positive scaling, and this is quite consistent with the stream flow scaling. That means, yeah, the stream flow scalings are more or less matching with the sub-hourly precipitation than daily precipitation. Sub-daily precipitation than daily precipitation. So low duration rainfall are becoming very important for stream flow. Now, what we try to do is that we try to check it with smaller catchment and larger catchments. There is a reason for this, because if you consider a sub-daily scale precipitation which are getting reflected in stream flow, so this sub-daily precipitation, it has to affect the stream flow immediately. The catchment size has to be smaller, the hydrological catchment size. So what we considered is that we have considered less than 1,000 square kilometer and more than 1,000 square kilometer. When you're considering less than 1,000 square kilometer, you can see that daily extremes and 3-hourly extremes, they are actually following each other. And then if you're considering greater than 1,000 square kilometer for stream flow, you can see that your 3-hourly extremes are actually dropping, because it takes for the stream for a higher watershed, this stream flow takes a lot of time. But what is happening is that for daily scale it's actually showing. So what I'm trying to say is that if the watershed is small, the sub-daily precipitation extremes are actually playing a very major role, which is quite reflected here. You can see this is the flow temperature scaling rates for different watersheds, and these are the area of the watershed. You can see that the flow temperature scaling rate is quite high when the area is less than 1,000, but after that it is becoming almost flat. So it's not really very high. So that shows that the for smaller watershed, sub-daily precipitation really affects, and this sub-daily precipitation has increased at a very high rate, sometimes at a Clausius-Clapeyron rate, sometimes at super Clausius-Clapeyron rate, which has been reported, and this needs a serious attention. So it's not just daily precipitation. For extremes, we need to understand the sub-daily precipitation characteristics as well. Now, when we are looking at extremes over India, of course, it starts with one of the very famous paper by Goswami et al., which was published in Science, and it shows that over the central Indian region, which is kind of sort of homogeneous, it shows that the extreme precipitation has increased quite significantly, whereas the moderate rainfall has reduced. But if you look into the spatial variability of extreme precipitation, the spatial variance also has a strong increasing trend, which we published in Nature Climate Change long back in 2012, where we have shown that the spatial variability has been increasing. That shows that the extreme precipitation characteristics of one point is becoming more and more different from the neighboring points. And this probably shows that not only just the global factors, the local factors are also very, very important, and we need to consider them. Now, if you're considering several local factors, of course, you have been working on many of the local factors like land use, land cover change, water management, etc. But here I'm just focusing on the urbanization part. These are the 4 local factors that affects the extreme rainfall, but we're just focusing on the urbanization part. And of course, urbanization may affect the extreme rainfall through urban heating, through urban heat island effect, through aerosol, and also through these 3 are kind of well known, but the 4th one is through urban structures that results into more eddies and instabilities. So I'll just focus a little bit on that. So what we did here, we have we know about the Mumbai region. I'm just giving an example. In 2005 there was extreme flood, and in Santa Cruz the reported rainfall was 900 mm per day. I mean, in a single 24 hours the rainfall was 900 mm, whereas the Kolaba, which is around 23 to 20 kilometer away, that reported only 80 millimeter per day. So it shows that there is a spatial variation. So And of course, that was an exceptional case, but there are many cases that shows that, there is a huge spatial variability, specifically those who do a lot of driving in the Mumbai region, they know it very well. So what we wanted to do, wanted to do some work simulations with 27 kilometer, then 9 kilometer, and then 3 kilometer over the Mumbai region. And there are a lot of automatic weather gauge stations which are available over the Mumbai region, thanks to IMD for setting up all of them. So what we tried to do is that we tried to check with 3 cases of work simulations. The first one is we have not considered any urban canopy model. It's just simply taking the radiation. The second one, we have considered a single layer urban canopy model. Wherever there is an urban region, urban land use, we have replaced them with a single layer of building. And the third one, we are allowing, it's a very fine resolution run where we are considering multiple layered of buildings. That means buildings, roads, multi-stories, slum areas, etc. And we allow the drag and wake diffusion to take place. And when we perform that, what we are finding is that if you are considering the urban morphology, if you allow them to, to be included in the work simulation, this is actually quite well matching with the observed data set. You can see the observed is quite well matching. 96.30, it's around 102. Whereas for others, it's quite less, it's around 60. And the other important part, what we have found is that if you look into this plot very carefully, so I'll not take much time on it, but I'll just say that if you don't use any urban canopy model, this is the spatial variation, or spatial variability of rainfall. If you are using single layer urban canopy model, this is the spatial variation. And if you are considering the observations, they are far away. There is a blue one, and the green one is with the multi-layer urban canopy model. You can see that this is quite well matching. And this is the observed spatial variability, and these are with other 2 simulations, and this is with multi-layer urban canopy model. You can see that multi-layer urban canopy model is actually showing the higher variability, which is matching with the observed data set. And that is because of the urbanization, because of the urban structures, buildings, etc. Because of their structures, the diffusions or instabilities are formed at certain small areas over the urban region. These are the hotspot regions where we'll get a lot of rainfall, not everywhere. And because of that, you'll get a very high spatial variability. So if you have a non-urban region, the spatial variations will be small. But if you have high urban regions with a lot of different urban structures, then you will get this kind of with a very high rainfall at certain pockets of the urban regions. And this is also quite clear from this figure, where you can see if you consider no urban, this is the blue. A single urban means red, but if you are considering multi-layer urban canopy model with lots of urban structures, the spatial variability is increasing. And also it shows that if you go beyond 10 kilometers in an urban region, the spatial correlation actually drops down below the statistical significant correlation. That shows that in urban regions it's very important to take care of. We should have a higher number of stations to understand the rainfall patterns. Now, I'll now quickly go to one of the things which we've done after 2015. In 2015 we have a extreme flood in Chennai, and after that the principal scientific advisor to the government of India, then Dr. Chidambaram, came to IIT Bombay, and he asked me to take a lead to develop India's first real-time urban flood forecasting system for Chennai, and and there were actually 30 scientists who have worked from 8 institutes. The institutions are IIT Bombay was the lead, then IISc Bangalore, then IIT Madras, Anna University, IMD, INCOIS, NCCR, and NCMRWF. So we all worked together, and we completed in a record time of 1.5 years, thanks to my collaborators. In fact, Dr. Patanayak also was involved here. So I'd like to say is that this is the urban region. Why is it very challenging? I have already said that urban rainfall is a challenging task. In the upstream of Chennai, there is a watershed, there are reservoirs. Over the coastal region, there is ocean, there is storm surge, there are tidal effects. And within the urban region, there are a lot of complications in terms of refined urban structures, fine resolution, DEM, drainage, etc. So it was a very extremely complex task. And we have, this is the framework which we have used. We have the rainfall, we have used the NCMRWF rainfall forecast for up to 72 hours, and we have used some radar data for nowcasting. These are the coastal conditions which has been provided by INCOIS, the tidal and bathymetry, the tide surge forecast. The hydrologic modeling was in the upstream of the city was developed by the IIT Madras team, and the urban flooding was done by one of my colleagues from IIT Bombay, Professor Shubhankar Karmakar, and then we did a proper 3D visualization for inundation forecast. So first, for we have used the quantile regression because the standard regression doesn't give us the proper thing. It gives the mean rainfall. So we have used the extreme condition. We have used the quantile regression to get the rainfall at a station level, and this is the performance. So this is the flood model performance, and you can see that sorry, I mean yeah. So and this is the flood model. So we have developed different. So in the flood model, we have used different shapes of grids, different types of grids, and this is as the resolution was as small at few meters at certain points. So we have to use those things to represent the bathymetry and everything, which is a very complex stuff. It takes a lot. It takes a lot of time to run a flood model, I'll tell you, because of this fine resolution model. And we checked it with the 2015 recorded flood data, which was taken from watermarks, etc. And we have found that for 80% of the points, the error is less than 1 meter. And we are kind of happy because when we talk to the disaster mitigation people, they said that, I mean, very micromillimeter level kind of accuracy is not required. A meter level accuracy is more than enough for any kind of evacuation operation, to make a decision on any kind of evacuation operation. So we are kind of happy because of now. The other thing is that if you run a flood model, it takes a long time if you really seriously run an urban flood model. And so what will happen if you use this urban flood model? What will happen after we'll get the forecast after the flood has already occurred. So we didn't want that. So for that, what we did, we have generated a data bank of simulations. So we have considered multiple cases of rainfall return periods, storm duration, the past condition, tide condition, everything. We have generated 800 simulations, so that what will happen, let's say at 3 p.m., if the forecast is getting ready at NCMR WF, by 5 p.m. we'll do quantile regression, statistical downscaling, everything, which is being done actually in automated way. And at the same time, the model will automatically take the tide forecast, the upstream hydrologic forecast, and past condition from IIT Madras, and then tide forecast from INCOIS and so on. And then it will try to match from the flood data bank for day 1 and day 2 and day 3 what are the closest condition. And based on the closest condition, immediately at 5 p.m. it will give the flood inundation maps for 3 days. So this will not taking any kind of computing effort. It just immediately provides. Now, so this is working like this. This is the forecasted rainfall compared to different percentile levels. This is the forecasted tide and past condition. And based on that, it will search in the data bank and it will give the flood inundation level. Now, let's say if there is a forecasted inundation and 99% is showing a flood inundation, then it will not stop. Then it will start the real-time flood modeling, which will be done at NCCR. We have shared all the codes, everything with NCCR so that they can run it. And in the NCCR, the real-time simulations will start, which will update every 6 hours. So the updated flood profiles will be given, and accordingly updated forecasted flood profile will be given, and accordingly decisions can be made. And this is the way it will look like. So let's say this is the initial condition and this is the forecast day. So 80, 85, they'll show no flood. 90, it will show some flooding regions. And if you click on the flooding regions, then we have made it in such a way so that you can go even at a building level. With a Google map, you can go at a building level and see that how much area is getting flooded and how much area, which buildings are most likely getting flooded, etc. So this kind of information, even at that level, it is possible. And we have generated a 3D visualization that can be used for getting the flood inundation. And actually, this method, we designed this, we developed everything, and we shared all the codes, everything to NCCR, and NCCR is now doing the operational forecast with the models which is developed by this team. And NCCR has also followed exactly the same methodology for Mumbai flood forecasting, which is also inaugurated very recently. So thank you. And then as summary, as I was telling that, extreme rainfall is a very complex thing. So it's not just the global factors, global and local factors, both needs to be considered. And based on that, we should come up with a better forecasting system and evacuation techniques. Thank you for your patience. I hope I stick to the time, and thank you for patient hearing.
Yeah, thank you very much, sir. Actually, you have plenty the time also. There are no need for us to tell anything. Yeah, and also you have highlighted the urban flooding issue of inundation modeling so very nicely. I think there are maybe some questions. Can you read out somewhere, reporter, please?
Sir, no messages are in chat box. No questions are in.
Okay, so sir, for urban, particularly since you are also in Mumbai, so how because every season we are facing this problem, particularly in Mumbai. So focus to Mumbai means how we can handle this urban flooding, all these things. Can you elaborate? Because IMD also working with that flow, all this thing. But whether really it is giving some means visible progress or not, that's all. That is.
Yeah, I'll tell you. I think that's a very interesting question, actually. I'll tell you first with Mumbai. So Mumbai in 2018, 2019, I was closely following the forecast, and what I have found is that, we know that all the models have a certain bias, and we have to work on the bias. So we cannot really get the perfect forecast. But what is being happened is that every time what was happening is that after the extreme rainfall is taking place, the next day is forecasted as an extreme rainfall. So what was happening is that all the schools, colleges, there was, they were closed on the next day of the extreme precipitation, not on that specific day. So this is what, in fact, I talked to Dr. Mukhopadhyay of IITM Pune also. I reported this, that this is something, there is a daily bias, 24-hour bias, and because of which, by the time the extreme rainfall is already taken place, we are getting the forecast, and next day it's a sort of a holiday for everyone, but it's no rainfall. Sometimes it's actually no rainfall. And but what I have found is that many of the Mumbaikars have noticed it, and what they have started doing is that in 2-3 days before, if they are getting a forecast for extreme rainfall, one day before they are getting alert. So they were kind of designing their own mental model to really take care of the forecast biases, which was very interesting part, which I've found interacting with many of the people, in fact inside our institute, and also many of the guardians of parents of my kids' school. So they are also following the same thing, so which is very interesting. But the most important factor I feel is that if you really need to understand this kind of patterns, we should have first a very good amount of hindcast is needed. So the hindcast will give us an idea over a longer period that in what way the forecast has performed, or what are the small problems which the forecast have, which is impossible to really resolve by a model at this stage. But we can do some post-processing to process it. The second thing is that Mumbai drainage data, finding Mumbai drainage data is extremely difficult task, because it's probably this drainage plays a major role, and that's another issue. I'm sure, because in iFlows I was not involved, so they have used the model, but I was not involved in that. But I have heard that, because many of the MMRDA people also have said that this needs more improvement, etc. So I think this also depends on because models can do, given if there is a good data is given, so that input data is also we need to include. And yeah, so these are the things I think which are very important. Proper inputs are given, proper hindcast, then of course we can keep on improving the forecasting model.
Thank you very much, sir. Tagi sir, would you like to say something, a comment?
Yeah, Subimal, thank you for sharing path-breaking research and the application of this in Chennai and also being followed in Mumbai. I got two observations. One is, you see, the events which you have brought out of typical Colaba, Santa Cruz, they are rare events. We don't have such recurring events, though spatial variability is there. But if you look at the long-term annual mean data of rainfall, there is not much of spatial variability is seen. So, so we'll have to look, very rightly brought out, yes, the spatial variability in the urban area is bound to be there. But at what degree is there with the improved? I see earlier we used to have just 2 or 3 observations in the city, so it's very difficult to bring out. Now with denser network of automatic rain gauges, you can really map these things and then see the model how well it is simulating. So, and I'm sure, as you brought out, is a continuous exercise to improve the models with good quality data. So we need to continue to work, which you have initiated, with good amount of data, and I'm sure IMD and other operational agencies will positively benefit and also make use of it. So this is one observation. The second thing which is there, the capacity building of these in this field both at the climate level of the global and you have brought out the local factors. These two also is equally important. See, we have to take a holistic view, global, regional, maybe sub-regional, and the local. So how this is, and this is not going to be uniform template for all the places. So I am sure younger people will look into the local peculiarities, the regional, sub-regional, with the global background. Thank you, Subimal.
Thank you so much, sir.
Thank you very much, sir. So for your nice, wonderful talk. Thank you once again.
Thank you. Thanks a lot.
So now we'll go for the next talk by Dr. Beena Balan Sarojini. She will be talking about Earth system variability and predictability, observational impacts and challenges. Over to Beena, madam.
Thank you. I'm trying to share my screen.
Yeah, please share here.
Can you see my screen in full
Yes,
screen
yes,
mode?
we can see. Go ahead, please.
Yeah, thank you very much. First of all, I would like to thank the organizers of the meeting to invite me to talk on this topic here. And I also like to thank the chairs, Dr. Patnaik and Dr. Tyagi, for chairing the session. The title, as it says, is Earth System Variability and Predictability, its observational impact and challenges. So I work at the Earth System Predictability section of the research department at the European Centre for Medium Range Weather Forecast in Reading, in UK. So Earth system variability and predictability is a vast topic. Today, I will be talking about observational impact of two parts of the Earth system, which is ocean and sea ice components of the Earth system. Outline of my talk, the first part of the talk is about impact of ocean in situ observations on the ECMWF subseasonal to seasonal forecast. And the second part of the talk, I will cover impact of satellite sea ice observations on ECMWF subseasonal to seasonal forecast. So the methodology used in answering this research question is the same for both the parts. First, we do assimilation experiments with ocean sea ice reanalysis. And then we look at the impact. We can take out each observing system in the initial conditions, and then we can look at the impact of this changed initial conditions on coupled forecast of ocean and atmospheric mean state. I will come to the details of it soon. So the first part is impact of ocean in situ observations on the subseasonal to seasonal range forecast. It's the work we have been doing at the Earth System Predictability section, and it's a work in progress. So these experiments are conducted using ocean observing system experiments, which is familiar to numerical weather prediction community as OSE. Before going to the details, first I would like to just introduce the ocean sea ice reanalysis system called ORA-S5, which is the current ECMWF ocean sea ice reanalysis. And this slide mainly shows about observational impact on the ORA-S5 initial conditions. So on the left-hand side, we see a sample picture of ocean in situ observations we get to assimilate in the ocean sea ice reanalysis. This is for February 2019. And these are total number of observations, about 4,400 observations after quality control. The green dots, as we see, is the coverage due to Argo observations, and the red are tropical moorings in different ocean basins. So as we can see, post 2005, after the advent of Argo observations, Argo observations cover most of the global oceans. And there are XBT and CTD observations and mooring observations as well. But they used to provide more impact on the reanalysis before the Argo period. And on the right-hand side, I'm showing root mean square error in upper 1,000-meter temperature in the ocean. So the left-hand side shows RMSE in upper 1,000-meter temperature, and then the right-hand side shows the observational density per month. The black line is showing the reduction in root mean square error over the years starting from 1975 to 2018. We can see that the root mean square error has reduced over the time. But if we look at the red line, which is the ORA S5 initial conditions, where these observational types are assimilated. So if we can look at different colors, post 2005, we see the observational density of Argo over dominates the observing system network. And there is no need to introduce ocean sea ice reanalysis, but for youngsters who are not aware of it, I would like to just say that historic records of ocean climate, they are in growing demand because we need it for monitoring ocean climate, and also we need to we need ocean initial conditions and improved and realistic ocean initial conditions to start initialize weather forecast ranging from days to weeks to seasons to decades. And this, for example, I'm not showing here the picture, but without these in situ ocean observations, we would lose about 1.3 months of lead time in ENSO prediction in the current seasonal forecasting system at ECMWF, C5. Now going to the experiment details, as I said, observing system experiments are ocean data assimilation experiments where we remove each type of observations from the initial condition. So that OC reanalysis would be where observations are removed in the initial conditions, and OC reforecast would be coupled atmospheric ocean land surface wave coupled system, and the reforecast where these initial conditions are used to start the forecast. So the ocean has 1 degree resolution, which is lower than the operational ocean resolution, the current operational ocean resolution. We keep the SST constraint on in all the experiments. There are 5 members and it's run from 93 to 2015. The reference experiment has all observations except the altimeter observations assimilated. Then we have no Argo, where Argo observations are removed, no XBT and CTD, where XBT, CTD are removed in the initial conditions, no tropical moorings, where the tropical moorings data are removed, and no in situ, where all the 3 observational types are removed in the initial conditions. And the first I'm going to talk about the impact on a seasonal couple forecast. They are 15 ensemble members, carried out for 15 ensemble members, and for May and November start months. Same experiment names where we initialize these reforecast with the degraded initial conditions to say. The results are shown for post-Argo period so that I could compare the impact of Argo and no in situ. I'm showing the impact for 2005 to 2015, that's a post-Argo period. These model outputs are available for the community for example, regional evaluation using independent in situ observations. So we are welcome for collaborations. The first slide, so it's the first time we are looking at the impact of ocean observations on atmospheric forecast at the ECMWF. So this slide shows the impact on seasonal range. I'm showing it for the ocean mean state first. The forecast are shown for June, July, August. If we focus on the bottom panel, we can see the methodology is looking at difference between these experiments. We can tease out the observational impact. So the top, the bottom panel shows the sea surface temperature impact. If the top two subpanels in the bottom panel shows May initial conditions, which the JJA forecast has started. And the bottom two panels shows the impact in the coupled forecast. So if we look and on the extreme right is the current bias in sea surface temperature in the reference forecast where all observations are assimilated. And if we focus on the observational impact on the left side, we can see that for the sea surface temperature initial condition, the impact is small, but if you can see the stippling, the impact is significant. Removing observations, if we look into the bottom panels, we can see that the changes in no in situ, for example, the no in situ impact, that largely remains into the forecast, the JJA forecast. And also we see that cooling happens when we remove in situ observations. So the model, the forecast model tends to reach its model bias when we remove the observational constraint. And we also see that out of all the observation systems, Argo has a large impact for over the no in situ impact. So I have only shown no Argo in the results shown here. And these observations, these removing observations, the cooling we see, they're likely due to mixed layer processes. We also see strong dynamical cooling in Pacific cold tank area, which is also seen in the no Argo impact. The no in situ impact is large because of two reasons. Because these experiments are started in '93, so in situ observations have been removed since '93, and I'm showing results for the post-Argo period. Whereas if we remember the previous slide where I showed the observational density, 2005 onwards, we have the Argo observation. So the no Argo impact is only happening since 2005. If we look at the top panel, that is ocean heat content, which is an emerging climate quantity showing rapid warming. Again, similar plots, the current bias is seen on the extreme right of the top panel, and top two panels shows May initial conditions with which the forecast is started. We can see that the difference in ocean heat content, they largely remain into forecast, and no instinctive impact on initial conditions are larger than no Argo. And we also see that the compared to the existing bias in the reference forecast, in the Indian Ocean, the ocean heat content impact when we remove in situ observations, they have opposite signs. So the patterns of bias and observational impact, they are not same in the nonlinear system we are dealing with. But we can see that the observation and the magnitude of the observation impact, they are commensurable to the magnitude of the bias we see in the in the forecast, indicating the value of in situ observations in monitoring key climate quantities. So this is an example slide to show the observational impact on seasonal range again, but this time on the atmospheric mean state. Similarly, it's a May started forecast for the post-Argo period, June, July, August forecast shown. If we look at the bottom panels, we can see that the first and second sub panels, they show the no Argo and no in situ impact due to removing Argo and all in situ observations. The 2 meter, this is the 2 meter temperature changes. As we can see, these are very similar to the sea surface temperatures we saw in the earlier slide. 2 meter temperature also shows largely cooling, overall cooling, no in situ impact is largely similar to no Argo. If we look at the top panel, these are mean sea level pressure impact. Again, tropical Pacific, we can see the removing ocean in situ observations, the mean sea level pressure has increased, and they are also associated with La Nina-like conditions, and we also see dryness, reduction in precipitation. So if we look at the tropical Indian and Pacific regions, these mean sea level pressure, they are likely due to large scale SST gradients. And if we look at the extratropics, this could be likely due to teleconnections through some local impact from the Gulf Stream region and also from tropics or subpolar jet. The second part is about observational impact on the extended or subseasonal range. Similar initial conditions as I explained before, and the atmosphere is about 36 kilometer resolution and 1 degree ocean. We do 5 ensemble members for the subseasonal range, and these the forecast are started for all months. Again, the maps I'm going to show are for November started forecast, and week 4 impacts are shown, just to show observational impact in the subseasonal range. So they are, we saw the impact in the seasonal range for the 3 lead months. Here I'm showing the 4th lead of 4th week. So again, top panels shows sea surface temperature and sea surface salinity bias in the reference experiment where all in situ observations are assimilated in the initial conditions. The bottom panels show no in situ and no Argo impact. If we focus, the hatching indicates positive significance and stippling indicates negative significance. Here, because we are removing observations, we're looking for stippling, which shows that negative impact or a degradation in forecast. Similar to what we saw in the seasonal range, we see cooling in sea surface temperature, mostly over the extratropics in both hemispheres, and also we see that overall freshening happens over the warm pool region and global tropical oceans. It's similar to that, no in situ, no Argo is contributing more to the no in situ impact. The observational impact on subseasonal range for subsurface ocean state. Here I am showing the mixed layer depth calculated based on vertical density criterion, and on the left and on the right, the top 300 meter average temperature. We can see that the observational impact, they in the mixed layer depth, they shows shoaling, especially for the northern extratropics, and slight increases in mixed layer for the tropical regions. So they are these are fast processes happening, and mean mixed layer processes have changed. And the top 300 meter changes we see in no in situ and no argo impact, they are very similar to the ocean heat content changes we saw in the seasonal range. And they're also similar to sea surface temperature change. And we see in the next slide. This is the impact on subseasonal range for atmospheric mean state. On the left-hand side, we are seeing the impact on 2 meter temperature bias. They are very similar to the sea surface temperature biases. And also we see the impact is small, but they are significant. We also see upper atmospheric variables like 200 hectopascal stream function. But they are mostly localized over the northwestern American continent in these experiments where we used 1 degree ocean resolution. This is a summary slide showing the observational impact on the subseasonal range on both ocean and atmospheric biases. Red means a regraded mean state compared to a reference forecast. These are shown for both northern hemisphere and tropics. We can see that in lead time from week 1 to week 4 in different ocean variables, surface and subsurface, there is significant degradation in the mean state of ocean forecast. On the right hand side, we see similar in impact, but the atmospheric impact is small. But we can, if we look at deep red triangles, we can see that for tropics, surface temperature, mean sea level pressure, and 500 hectopascal geopotential height and stream function at 200 hectopascal have significant, small significant degradation, which we also see on a smaller scale in the NOAAGO impact. So the first part was focusing on the degradation or observational impact in both seasonal and subseasonal range due to removing in situ ocean observations. Now the second part, I'm going to show how satellite sea ice observations are going to affect coupled forecast.
Please be quick, please quick. 3
How
to 4
many more
minutes.
minutes?
Okay.
How many more minutes?
3 to 4 minutes you can take.
Yeah.
Right.
Okay. Thank you. This here I'm mostly focusing on impact of thickness initialization. So we have sea ice thickness observations, recent multi-sensor observations for both thick ice and thin ice. It's called CRISAT-2 SMOS dataset. And availability of this data set for Arctic wide region has given the opportunity to constrain sea ice thickness observations in the ocean reanalysis for the first time. So if we look at initial conditions on the left-hand side, it's March and November forecast at the bottom panel. March initial conditions and November initial conditions. We can see that both overestimation and underestimation exist. There are huge biases of about 1.4 meter in the initial conditions where no sea ice thickness constraint happens. And when a sea ice thickness constraint is applied, we can see most of the biases are removed. And on the right hand side, I'm showing a bias corrected mean absolute error in sea ice concentration forecast. Round solid dots show the impact, significant degradation, significant improvement in forecast when we include sea ice thickness observations. This is for lead month 2 to 5. Here I'm showing the impact. Left hand side is a new sea ice matrix, relatively new, called integrated ice edge error. They have the advantage of decomposing it into over prediction and under prediction. And on the right hand side is the 2 meter temperature impact. So we can see that blue means significant improvements. So we can see that there is significant improvement in ice edge and both 2 meter temperature for the autumn forecast, which is started in spring. And we also see slight degradation in autumn forecast started at the end of melt season. This is an example slide showing the impact of sea ice thickness initialization on the subseasonal range. The left-hand side, again, solid round dots show lead month forecast where the impact is significant. We can see significant improvements in spatially integrated forecast error for ocean north of 50 degree north, which is mostly the Arctic and Pan-Arctic region. So it's a busy slide, but the main points I would like to stress from these observing system experiments is that ocean in situ observations, they have a profound and significant impact on the mean state and of both ocean and atmospheric forecast, and they are categorized. They can be categorized into two parts. Which is a fast process. We see in the subseasonal range, they are fast changes due to changes in mixed layer in the ocean initial conditions. And we also see medium and slow changes due to large scale SST gradients, changes in large scale SST gradients, for example. Then the impact is not always linear and cannot be translated into improvements because the biases are not just occurring due to SST errors. It also occurs in forecast due to biases in other parts of the Earth system. The spread, when we remove in situ observations or satellite CX observations, the spread is predominantly decreased. And we also see the 5, when we use 5 ocean initial conditions, only the spread increase is decreased. The adding sea ice thickness constraint in initial conditions, they reduced the current biases in sea ice forecast in our system, seasonal forecast system, and it also gives a predictive skill of Pan-Arctic sea ice for lead times of up to 7 months. The main takeaway messages of my talk are listed, the 3 points at the bottom of the slide. We see that importance of these results demonstrate the importance of initializing ocean mixed processes by initializing ocean mixed layer. We also see the value of consistent, uniform, and deep-reaching global ocean observational coverage for both operational forecast improvements and also for frequent climate monitoring services. These role of ocean observations on the atmospheric forecast in the subseasonal to seasonal range, they also point to the need of robust and up-to-date assessment of ocean observational impact in forecasting systems using observing system experiments. And at the moment, I have mainly focused on mean state changes. There are also changes in forecast skill. Some of them I covered, but because we see a relatively small observational impact in atmospheric skills, I am currently doing these experiments in the operational ocean resolution using the latest ocean sea ice reanalysis. The final point is obvious. An Earth system approach is the way forward if we were to monitor and predict climate variability and extreme events. It's very important to cover all the topics, but I think I have covered my current work. I also listed some of the past work I have been involved, listing some of the relevances for our meeting now.
Okay, thank you, Dr. Balan. So I think, yes, you have shown an interesting topic, means ocean observations, particularly ECMWF, centralized ECMWF, they are focusing on subseasonal scale prediction, improvement of subseasonal scale forecast. So probably this also should contribute towards that one. I feel so. Means improvement.
Yes. I am showing this impact basically to improve our reanalysis system, but also they have advantages for observational communities to improve observing network, so that we have a consistent record. And one of the problems we see with our ocean reanalysis data sets is consistency in temporal changes, and these are so this hinders robust assessment of long-term trends and long-term changes, and these mainly occur due to changing observing system. That is what I'm trying to address here.
I think thank you very much for your wonderful talk. Actually, we have little lack of time. But Tagi Sahab, if you would like to quick comments or something.
No, it brings out importance of ocean observations for sub-seasonal forecast. So I think observing the systems needs to be augmented, and beyond, is it also required for the climate variability and climate change projections also? I'm not sure. Part of, but positively for sub-seasonal, seasonal predictions, these initial conditions are important, and which is again highlighted here. Thank you.
Thank you.
Yes. But, may I just comment on Dr. Tyagi's point? Yes, as I noted in the introduction, they have two purpose. One is to monitor climate on real time. These are the reanalysis. We have ocean monitoring charts available at our webpage, and also the subseasonal to seasonal prediction data sets available for assessing extreme weather events.
Okay, sir. Thank you, Dr. Jala, for your wonderful talk. So if there will be any question, I think you can interact with them. They will write to you. Okay, because shortage of time, we are not further enhancing. Thank you once again.
Yeah, thank you very much.
Yeah. Now we'll go for the next talk, invited talk, that is Dr. Ramesh Kumar Jadhav. Please. So this is around 12 minutes will remind. Okay, Jadhav ji.
Yes, sir.
Yeah, please go ahead.
How much time?
Total 15, so including discussion, I think. Yeah. So
okay.
1 or 2 minutes, please keep it.
Okay. I am sharing my screen. So, namaskar. Is it okay? My screen is. Are you able to see?
Yes, we can see. Please go ahead.
Okay, no. Okay, fine. So now I am going to talk about relationship between Azure High and Indian summer monsoon. So actually, during summer monsoon season, that is from June through September, we know that Azure High in the Atlantic, North Atlantic Ocean, it is in it attains its maximum strength and it is bigger in size. So in this study, I have tried to link the Indian summer monsoon with this Azure High, means try to find out the relationship, that there must be some relationship because both of them are peaking during the summer season. So, so we know that during Indian summer monsoon's time that the maximum precipitation zone that shifts from North Atlantic to northeast of India, and there is a very intense precipitation that that causes large scale outflow at the upper troposphere and large scale and intense convergence in the lower troposphere. So that large scale outflow in the upper troposphere, that we call it as Tibetan High. And this Tibetan High, sometimes it reinforces it is a large scale divergence in the upper troposphere, and it also reinforces the convection. When it shifts from west to east, it also shifts the monsoon accordingly. So, and as I mentioned that in the North Atlantic, we see a semi-permanent feature during monsoon season, that is last subtropical Azure High, which is a large subtropical center of high atmospheric pressure due to enormous large-scale subsidence and sinking motion air in the system. So here means you can see that during winter season, this Azure High is not that much strong, but in the summer season, this it attains its maximum size and it is more powerful. So I have tried. So I have tried to find out that the relationship between these two. So for that, that means this is just an introduction that in the upper troposphere you can see that 200 means this is 200 HPA geopotential height and 200 HPA divergence. So here you can this shows the extent of this Tibetan High, and here there is large scale divergence at the upper troposphere, and at the same time here in North Atlantic you can see there is large scale convergence over this region, and also means at the upper troposphere means this contour shows the jet streams, and this setting shows the vorticity. So the north of this jet streak you can see positive vorticity, and south of the jet streak there is negative vorticity. But here in the North Atlantic, because there is two jet stream present in North Atlantic, one is American jet stream and another is this Asian jet stream, and because of this here we see that there is a quadrupole type of structure in the vorticity, and so North Atlantic is more vibrant during summer season. So it must have some relationship with Indian summer monsoon, and also we can see that this is showing the Rossby wave path, and it is this North Atlantic is is situated in the path of this circumglobal Rossby waves, which is circulating all in the northern hemisphere. So for that region also this becomes very important, that if something is happening in North Atlantic, it will influence our Indian summer monsoon. And this shows the Rossby wave source. So because of this subsidence over here, in the North Atlantic, it is also a region of Rossby wave source. And in these studies, for the upper troposphere, I have considered different levels to represent the upper troposphere. The reason for that is that that zonal wind that strengthen that attains its maximum strength at 200 HPA. So for jet streams, I have considered 200 HPA level. For divergence, you can see it attains its maximum strength at 250 HPA. For vorticity also at 250 HPA, and for this this NN, it attains its maximum strength at 300 HPA. So for this region, I have considered different tropospheric level for this different meteorological parameters. Now, I have done this UF analysis over this that Indian landmass, excluding this Northeast India, because for the reason that Northeast India is out of phase with the all over India rainfall, and also because of excessive loading, because the rainfall is very high over here. So this is the first UF. It accounts some 18% of variance, and this is the correlation with all over India rainfall. So here you can see that it is showing positive rainfall anomaly over this central India and western India, and negative rainfall anomaly in northeast and east India. And this is the correlation with upper tropospheric geopotential height and wind. So here means you can see that this center of actions are what we call circumglobal teleconnection patterns, and this is because of Indian summer monsoon and desert relationship. So here over the North Atlantic, we find relationship positive geopotential, significant geopotential for, and this is just situated over the Azure High. So and at the lower troposphere at 200 HPA, 850 HPA and mean sea level pressure, here you can see that it is showing positive correlation at the same place where at the upper troposphere it is showing this positive correlation. So, and here that atmosphere is equivalent barotropic. So because of that, here means we are getting the same sign, and here over the Arabian Sea we are getting negative mean sea pressure, mean sea level and pressure anomaly, and that is because means this Indian summer monsoon has shifted westward. It is more active in western India and central India, and less active over this northeast India. Basically, the monsoon has shifted westward. So means this for further study, I have considered this region because we know that the Indian summer monsoon is having a relationship with circumglobal teleconnection pattern that is showing this spots, and there is having a relationship between Indian summer monsoon and desert relationship. So this is new. So I started to explore this one, and that is Azure High. So I considered that region. I considered mean sea level pressure over this box, and did the same analysis for 200 HPA geopotential height and wind. So you can see that here it is obvious that it is showing high pressure and high pressure anomaly over here, and these are again that circumglobal teleconnection pattern, and this is monsoon desert relationship, and over here you can see that it is showing negative pressure anomaly at the upper troposphere just below this one, and negative pressure anomaly over here. So I tried to find out that how this is affecting Indian summer monsoon. So and here means this is the correlation with 500 HPA omega. So it is showing significant positive anomaly. That means that a strong subsidence over this region, and that is that we know that Azure High is a region of a strong subsidence, and when Azure High is strong, it means that subsidence is strong, and because of this strong subsidence, it will be associated with upper troposphere divergence. So this is 250 HPA divergence. So these are related to each other. Means this strong subsidence will cause this upper troposphere divergence, and this is Rossby wave source. As we have seen that because of this upper level divergence, it will amplify this Rossby wave source. So this region, this North Atlantic, becomes the region of Rossby wave source. That means Azure High, Azure High is intensifies, it becomes source of Rossby wave at the upper troposphere. And this is the correlation with 250 HPA vorticity and 300 HPA, this burnt Vesla frequency NN. That is the measure of stability of the fluid to the vertical displacement. So here what we are seeing that here means this is basically showing that it is intensifying this unstable atmosphere from North Atlantic, and it is generally trapped, and it is moving trapped up to this North India, and it is extending up to East Asia. And here that vorticity, you can see here it is positively correlated, negative, positive, and basically it is intensifying this jet stream. Here you can see that this upper troposphere geopotential height is here it is positively correlated, and because of this this is the path of the Rossby wave source, Rossby wave activity in the mid latitude. So because of this cascading down of this Rossby wave, it will produce negative anomaly over here and positive anomaly over here. And this negative anomaly will intensify this jet stream over this region. And this negative anomaly will intensify the jet stream at its entrance level. So, so here these two low pressure anomalies are intensifying this jet stream over this region. And because of this intensifying of this jet stream, and this is the region of Rossby wave source, so that low frequency and disturbances will travel along with this jet stream from this North Atlantic towards this Indian region. So here means what is happening means this Azure High is intensifying the Asian jet stream over this region, and also it is a region of Rossby wave source. So Rossby waves are amplifying, and it will carry this low frequency anomaly from this North Atlantic towards this Indian region, and like this both are connected. Means this is the teleconnection pattern. Means how this Azure High and Indian summer monsoon are related to each other. Means how this Azure High is influencing northern Indian summer monsoon. So this is the composite of this extreme Azure Highs. This is for excess years. So here during the excess years at the upper troposphere, what we are seeing that because of this intense Azure High, it forms this dipole type of a structure over this over North Atlantic. And that is because here this atmosphere is equivalent barotropic, and here it is tropic. Tropics is in nature. So here, when this azure high is much larger and intense at the over this region at means north of 50° north, it will have the same sign, means high pressure anomaly at the surface and high pressure anomaly at the upper troposphere. But over this region around 30° latitude, the sign will change because of this tropical nature. Here at the lower troposphere, it is high pressure anomaly, and at the lower troposphere, it is high pressure anomaly, and at the upper troposphere, it will be low pressure anomaly. So these two will form the dipole structure in the at the upper troposphere, North Atlantic. And because
2 minutes, 2 minutes.
Okay. And because of this cascading down of this Rossby wave activity flux, Rossby wave, here this negative, positive, and negative pressure anomaly will be formed, and this negative pressure anomaly will intensify this jet stream over this region, and this positive and negative pressure anomaly will shift this Tibetan high towards southwards, westward. And because of this shifting of this Tibetan high westward, our whole monsoon will shift westward. So like this, it is connected. While during deficient years, because this azure high is very big, so this dipole structure will not be formed in over this North Atlantic. Only here at the upper troposphere, this azure high is big, so at the upper troposphere, this upper troposphere geopotential is also showing negative, and this is the cascading down of this Rossby wave. But these waves are very weak, so during this negative deficient years, the influence of azure high over this Indian summer monsoon is very big. Here you can see this dipole type of anomaly is very strong, and here it is big. So the azure high influence is mainly in the excess years, not is very big during the deficient years. And this I have done EOF analysis over this region, and this is the second EOF analysis which explains 15.6% of variance. So it means it is to say that this type of structure do occur over this North Atlantic and Asian region, and over this region you can see that it is very weak. So this is all about and the whole story you can just go through this paper. It is already published, and it is in Nature Partner Journal, Climate and Atmospheric Science.
Thank you, Dr. Yadav, for highlighting this teleconnection talk, means how the monsoon is related to azure high. So people should do more research on this one. And
Yes,
thank
sir.
you. Yeah. So if there is any quick question in the YouTube, please we can have one.
No, sir, and no questions are raised.
Yeah. So let us thank you very much, Dr. Yadav. I think you have talked very nicely and doing good research. Okay. Thank you very much. Yeah. So actually we will go for now the contributory papers. So there is some one request is there. So one talk we are arranging first because they have to go for some validatory function international conference. So we are slightly rearranging. So we'll take the first talk Hemlata Bharwani from IMD, because she will be joining that one validatory function of WMO. Are you there?
Yes,
Hemlata?
sir. Yes,
Yeah,
sir.
please start. And the 10 minutes time is there, so 9 minutes and 1 minute for talk. Correct? Okay.
Thank you, sir. Thank you, sir.
Okay, fine.
And I apologize for the inconvenience. Sir, I think Yadav sir has to stop sharing.
Yeah,
sir.
please stop share. Jadavji, please stop sharing.
Okay. Now it is okay.
Yes, sir. Thank you, sir.
Okay. Thank you.
Sir, I hope my screen is visible, sir.
Yeah, visible. That's fine.
Thank you, and sorry for the inconvenience caused to other participants. I am Hemlata, working as scientist C in India Meteorological Department. The name of my paper is Performance of Flash Flood Guidance System over South Asian region. Just to quickly give you a background and introduction how this system came into picture. Sorry, I'll start my video also. Yeah, so it's IMD in collaboration with WMO jointly implemented South Asia Flash Flood Guidance System with US Weather Agency and USAID partners. So WMO recognized IMD as a regional center for South Asia for catering the flash flood needs. And the services are provided to other 4 countries, that is Nepal, Bhutan, Bangladesh, and Sri Lanka. So FFG services were dedicated to South Asia operationally from 23rd October 2020 by Secretary, Ministry of Earth Sciences, Government of India. So the main objective of the system is to provide location-specific flash flood guidance up to watershed level. I would like to specify the watersheds. Whole India is divided in up to 1 lakh watershed level of 3 to 4 kilometers each, on pluvial flash floods in the form of risk with 24 hours lead time based on numerical weather forecast of 00, 06, 12, and 18 UTC, and threats with 6 hours of lead time based on the near real-time observations. So the capacity building of national for the flash flood forecasting system is one of the objectives, wherein IMD takes the lead and trains all the forecasters all over the South Asia every year twice. And we have fostered regional developments and collaborations between NMHs, that is Nepal, Bangladesh, Bhutan, Sri Lanka, and India, and disaster management authorities. So this was in brief about the objectives. So just to quickly go through the cycle, that the system started in 2016, and now we are 5 years hence, and the system is fully operational and working in so already catering to the needs of the people here. So quickly going through the products which are there, there are approximately 36 products available in flash flood guidance system, starting with diagnostic, which are satellite, global hydroestimators from NOAA as this. Then we have a global merged gauge mean aerial precipitation 3-hourly merged. We have soil moisture. Then the FFG products, the model products that are based on the Sacramento model is the products are flash flood guidance value that is available every hourly. Then we have threats which are available every hourly for up to next 6 hours, and persistence flash flood threat which is available every hourly and for next 6 hours. Then we have forecast products which are based on NWP models. So these products are available for 3 models: WRF, NCOM, and GFS. And these are available every 3 hourly. Based on this also, we are generating forecast flash flood threats and risk for next 12, 24, and 36 hours as a preparatory product. So just to quickly go through, this is the interface of the South Asia Flash Flood Guidance System, wherein you can see all the products placed. But this is just one part of the interface. We can show you the detail in this later. And this is one of the finest map server resolution available, wherein you can zoom in up to any level of, and the 1 lakh watersheds are divided with the boundaries also. The boundaries available are district, sub-district, med subdivision, states, IMD country outline, and UN country. Also, there are other inputs we have already done as radar and other stations. So whenever we get a threat alarm, we zoom into that location, we check with all the parameters, and I'm happy to say that the now newly available system, which is just implemented 2 months back, is so finer that we can issue the warnings up to an local area also. So this is the input or amount of rainfall observations for more than 5,000 stations going into the system. And we have radars, 15 radars integrated and other radars in progress for very short duration for nowcasting also in this. This is just the format of the national and international bulletin. Being a regional center sector, we have the responsibility to issue the guidance to the national and the international partners. So this is done every day, 4 times a day at 00, 12, 6 and 18 UTC. And we generate these bulletins for South Asia all together for all the countries in one. So just to go through the main, coming to the objective of my paper's performance, I'll get you through the case studies where just for example, starting with Mumbai, the case study was of 9th June 2021, wherein we had a threat in the suburban Mumbai. As we know, Mumbai being a highly densely populated place. So going through the products, you can see we were having a persistently heavy rainfall of up to 11 centimeter observed from IMD rainfall gauge stations, and the soil was completely saturated over their area. That is, you can see this 0.99 means nearly to 1, that is 100% saturation. So the contributing things were also in place for the system. And then we had FFG. FFG is flash flood guidance value, the minimum amount of rain required to indicate the runoff. So only 30 was rain required over that area to cause the flood. And so we issued a warning taking to moderate to high threat areas over that area, indicating the orange warning. And we issued the warning at the right time in the afternoon 06 UTC, and we observed that 30 centimeter of rain occurred in the Colaba and Santa Cruz area, and the waterlogging areas were there wherein we observed the threat came true. So this is just one of the examples. Then we have Shivpuri. This was in detail. I'll just quickly go through the other case studies just to highlight how the system is performing in different areas of the country. One was from western part, and now we are moving to the central part, that is Shivpuri in MP. This year has been very severe in terms of rain. So this was the area, Shivpuri MP, wherein we received persistent rain of 32 centimeters, and the area was saturation. So you can see the final resolution. This is up to 2 kilometers. I'm going into high resolution, and we had FFG was very low, as in up to only 30 that was required only in 1 hour. So this resulted in a very high rainfall, and rescue missions were conducted by Indian Air Force area. PM themselves took a survey of that area, and we issued the warning exactly in the Shivpuri district over that area, that is the Shivpuri and Ashok Nagar. So you see the system has the capability to issue the threats, the forecasted threats 6 hours in advance for particular district also. Here, the MCs are means meteorological centers issue the warnings more finer than district, that is taluka level. So quickly going through the other case studies, there is one of the case studies in Odisha when the cyclone hit the area, Yas, and we issued the warning and the warnings were realized. Then there's another case study of Kerala recently happened in 16 October 2021, wherein again we are getting the threats up to finer resolution possible. All the contributing saturations were there, rainfalls were continuously receiving, and we have issued the warnings and alert prior. And this is one of the deadly raining causing up to 46 people death toll in Uttarakhand place, 40 centimeter of rain in 24 hours. So this was a very, you can say, event which hurt us because many of the people, were not able to be rescued on time. But we have issued, as an IMD, have issued the warning here. So this is in general the feedback of the countries where we get in, where they say that they are very much happy with the service IMD is providing them with the help of this, because we don't go by only the system. This is just a guidance system, but we as a meteorologist and hydrologist analyze the whole event with the help of our seniors in NWP, NWFC, that is forecasting centers, and then we issue a warning for the countries, because these are very high level threat issues which we issue to them, and they have to take urgent action on this, because the flash flood warnings can only be generated 6 hours in prior. So this is from Sri Lanka, and then we have our feedback from CWC partner. CWC, as in Hydrological Agency, includes our bulletins in their own bulletins. Also includes our so that because they also have a good wider approach among all the stakeholders. So they also share our pictures of the events on their Twitter page and WhatsApp group. So also we are catering to the needs of the World Bank. So they also find our bulletins very helpful as they have various plans which carry out ahead. So just summarizing this, like how is the performance all over in South Asia in last 3 years? This is our observation and this is our calculation based on the all the events which have been captured and missed. So there has been a success rate of approximately 70%, and there has been a false alarm up to 20% and 10% of the miss rate as of now in last 3 years of operationals. That is 19, 20, and 21. So I would like to thank Intromet and the organizing committee for giving me this opportunity to share about the work we are doing in IMD. Thank you, sir.
Yeah, thank you, Amlata, for highlighting how the fast flood guidance tool on the collaboration of WMO is working very well over the South Asian country. Thank you. I think this will also need to fulfill the future requirement. Yeah, if there is any quick question, the quick YouTube, otherwise we'll go to the next speaker.
No questions.
Okay, thank you, Amlata. Yeah.
Thank you,
yeah.
sir.
Dr.
Sir, yes,
Patnaik,
sorry. Sir,
okay,
thank you, sir.
good presentation, Hemlata. I just want to check up because the shelf life is very limited of 6 hours. How the on the ground people are being communicated? You see, you have got CWC and all those big chain, but real impact of and the response has to come from the ground for safety. And so, are we targeted warnings are being sent to that area where the flash flood warnings are being issued?
Yes, thank you, sir. Thank you so very much for your question, sir. I would like to highlight one point here. With the help of the NWP products, we are giving warning 36 hours prior for that area. And when it gets specific over the next 6 hours, we give a preparatory warning 36 hours in prior to the particular area through our NWFC section. And then specifically identified districts are given 6 hours earlier. So there is always a preparatory time, and then the targeting area is identified. So this are circulated by the meteorology MCs to all the stakeholders, disaster stakeholders, sir. So this way, right now, this platform is being used to first identify at the broader level what will be the risk areas in next 36, 24, and 12 hours, and then catering to next 6 hours, sir. Currently, this is the mechanism established, sir.
Okay, thank you. Thank you so much.
Thank you so much for your question,
Yeah,
sir.
thank you, Dr. So now we'll go for the next talk, that Dr. Ajil Kotail from QSAT, driver of extreme rainfall over the southwest coast of India. Please.
Can you hear me, sir?
Yeah, we can hear you. So 9
Okay.
minutes and 1 minute for discussion, please. Okay.
Thank you. Good afternoon, and I'm here. Okay, sorry, it's on my screen. Sorry. I hope the screen is also visible.
Yeah, it is visible.
Okay, good afternoon, and I'm here to talk in brief about the drivers of extreme rainfall over the southwest coast of India. And as we all know, in recent years, we have witnessed an increase in the frequency of torrential rains. And since 2018, extreme rainfall events and associated natural disaster like floods, landslides have become a norm in southwest coast of India. And there is an obvious change in the pattern of rainfall, and therefore it is necessary that we understand the factors that lead to extreme events. So we have taken up the study with these objectives to understand the life cycle of extreme rainfall events observed over the west coast of India and the large-scale conditions that modulate the extreme rainfall initiation and decline. And this is the data and methodology we have used in our study, and we have used basically ERA interim data, profiles of vertical wind, humidity, SST, mean sea level pressure have been used from ERA interim. So outgoing long wave radiation data sets have been taken from CERES, and we have also used IMD graded rainfall data. And our definition of extreme is based on the mean rainfall calculated over the west coast of India from June to September over several years. And the 95% of the rainfall is inferred from the area average time series, and those days where the rainfall exceeds above 95% are considered as heavy to extreme rainfall days. So I'm going into the results, and these are some of the results. And the figure on my left shows the trend in the rainfall occur over the west coast for various categories of rainfall, and the red and green lines are for heavy to extreme rainfall events, and as observed for other regions in the Indian subcontinent, the southwest coast also shows an increase in the extreme frequency of extreme heavy rainfall events. And figure on left shows the progression of rainfall observed over the west coast from 5 days, from day -5 to day +5. That is 5 days prior to 5 days after the extreme rainfall events, which is represented here as day 0. As you can see, the rainfall over the entire west coast is low from day -5 to day -3, and is on an average, it was about 20 millimeter per day over most of the regions. And however, a significant increase in the rainfall is seen from day -3 to day 0, and a twofold increase in the rainfall is observed on day -1 compared to day -5. And the mean rainfall observed on day 0 and day +1 over most of the regions is 80 millimeter per day, which is about 4-fold increase in the rainfall as compared to 5 days before the event. So if you look closely at this figure on the right, the evolution of rainfall from low to extreme over the southwest coast is systematic, so it is not random. And this shows the evolution of 850 HPA wind, evolution of as you can see, the 5 days ahead of the extreme events, the wind speed was lower, and it was around 10 meters per second over the west coast and eastern parts of Arabian Sea. And the wind picks up momentum as condition progress further towards extreme rainfall events, and increase in the wind field is twofold on event day, that is day 0 as compared to day -5. The elevated wind is seen to persist for 2 days, that is +1 and +2, and the reduction in the wind speed is observed thereafter, and slowly regaining the normalcy thereafter. I mean, a qualitative comparison between the wind speed at 850 HPA and the rainfall observed over the southwest coast explicitly illustrate that the rainfall increase is in tune with the increase in the wind speed. To understand as to what actually could cause this increase in both lower jet streams and rainfall, we have analyzed the outgoing long wave radiation, and the result is shown here. And the contours in the figure represent the relative vorticity contour at 850 HPA. And 5 days before the event, like here, the deep convective activity over the entire west coast and central India was lower, and Arabian Sea was low as compared to extreme rainfall day, and intense convective activity prevails over the southeastern parts of Bay of Bengal. And as time progresses, convection over southeast Bay of Bengal propagate westwards, and 3 days before the extreme rainfall day, the core of deep convective activity is found over central Bay of Bengal, with convection also deepening over central India, that you can see in this figure. The convective activity over Arabian Sea and west coast remain unchanged between day -4 to day -3, and however on day -2 and day -1, the deep convection observed to be active over this region in synchronous with the convective enhancement of central India. And convection reaches peak over the west coast and the southern part of Indian subcontinent on day -5 and day 0, and persisting till day +1 are observed for the wind. And these contours are the relative vorticity observed at 850 HPA. And 5 days prior to the event, that is the extreme rainfall day over the west coast, the strength of cyclonic circulation at 850 HPA over the northwestern part of Bay of Bengal was lower. And as day progresses, a gradual strengthening of cyclonic circulation is seen over this region. And on day -3, we can see a well-developed cyclonic circulation over northwestern Bay of Bengal, and with the northward propagating convective cloud clusters. The circulation strengthened further on day -2 and day -1, and on day -1 and day -3, you see a well-marked cyclonic vortex at HPA can be seen. And further from day +1 to day -5, if you observe that the strength of those vorticity decreases gradually. To know how the monsoon depression led to an increase in the rainfall events over the southwest coast, and we have analyzed the evolution of meridional gradient of sea level pressure between central India and southwest coast. And so what you are seeing on the left is the progression of meridional sea level pressure gradient. And I have also shown here the wind speed basically, and we see that there is a steepening of MSLP gradient. Actually, the wind speed observed over the West Cape is also in line with the steepened gradient. Similarly, what we are also seeing here is the humidity as well as the vertical velocity. And usually monsoon season, the lower tropospheric humidity is usually high, and however, as day progresses towards extreme rainfall events, the RH, the relative humidity values were close to 100%, is almost saturated, and an increase in the humidity, and then you can see an increase in the humidity from lower to mid troposphere, and this increase is in sync with the strengthening of lower jet streams. So regarding vertical velocity, the ascending motions are not so pronounced in the lower and middle troposphere 3 to 4 days prior to extreme rainfall day. However, a drastic change in the behavior of large-scale ascending motion can be seen when the conditions approaches towards extreme rainfall day. It is because of the increase in the humidity flux due to strengthening of lower jet streams caused by the steepening of the meridional gradient of sea level pressure, basically.
So 1 minute, sir. Yeah. You have 1 minute left.
Okay, okay, sir.
Yeah, please, sir.
Okay, so basically the whole process can be summarized as something like this. So first there is a monsoon depression developed over Bay of Bengal, and which propagate northwestward direction and intensifies the convection as well as the vortex over the central India and northwest Bay of Bengal. And vortex always develops during monsoon season, and we can see the vortex, but how this vortex get modified due to depression determines the extent of rainfall. And because of this intensification of this vortex, there is a steepening of meridional pressure gradient, and this can intensify the lower jet streams, and that would also bring the instability, which will result in the formation of deep convective cloud clusters over the west coast of India. And this results in the incidence of extreme rainfall events. Since the evolution of extreme rainfall event over the southwest coast is a gradual process, it is always possible that we can find certain precursors which can potentially improve the forecasting of these events. And what you are seeing here is various precursors that we have identified from different parts of the monsoon region, and this is showing the evolution, and we put a certain threshold for this for predictors, and identify and analyze its evolution. And as you can see that these precursors basically more or less changed in concurrence with the rainfall trend observed over the west coast. And this is the conclusion. And the extreme rainfall events are linked to development of deep convection, and strengthening of these parameters intensify the low jet streams, and which increases the humidity flux, which increases the ascending motion from middle to upper troposphere. And these events, what we found is these events do not necessarily occur during the active cycles of monsoon intra-seasonal oscillations, but are linked to northwestward propagating monsoon depressions. And signatures of extreme rainfall can be observed in several meteorological variables developing out different parts of the monsoon region, and a synergetic analysis of these variables may help in accurate and timely prediction of these events. And more details on this work can be found in this paper. Thank you.
Next, our mic is off.
Sorry. Yeah, so thank you. That's why I was already Kerala is getting good rainfall nowadays. So this type of study will be very helpful to understand that one. And so once again, I thank you for this time. Sir, Tyagi sir, any comments or anything? We'll go otherwise to the next speaker.
Please go ahead.
Yeah.
Thank you, Ajay.
So, any question on YouTube? I think people are not
No,
there.
sir.
Okay. So thank you, Ajil, Dr. Ajil, for your nice talk. Now let us go to the next speaker, Arun Kumar. Arun Kumar from RMC Guwahati towards impact-based forecasting in Kerala methodology and implementation. Yes, Arun,
Yes.
it is over to you now.
Yes, sir. Thanks, sir. I'm sharing.
Yeah, so 9+1.
Okay,
Okay.
sir.
Yeah.
Sir, is it visible?
Yes, visible it is.
So good afternoon all. So myself Arun Kumar, I'm currently working as a scientist in India Meteorological Department, Regional Meteorological Center, Guwahati, Assam. I would like to take this opportunity to thank respected DGM and also to the INTROMET committee for giving me this opportunity to present this particular topic in this prestigious conference. So in recent years, it is observed that the general public, the decision makers and the disaster managers are not satisfied with the usual weather forecast. So they are not at all interested in what the weather. They are interested in what the weather will do. Okay, thus our national meteorological services like IMD is now changing their usual way of giving simple forecast into impact-based forecast and risk-based warning. So that impact-based forecast will give an opportunity to the general public and the decision makers and on the disaster managers for act accordingly to the impacts expected from a severe weather. In this particular presentation, I am presenting actually a methodology we have adopted for issuing an impact-based forecast in the state of Kerala. Particularly in this particular presentation, I am giving for Thiruvananthapuram and Ernakulam districts, the methodology for Thiruvananthapuram and Ernakulam districts. So how we can actually give an impact-based forecast? As a forecaster, as a meteorological person, we are very much confident about the weather information, the current weather and the forecasted weather. So we are having that. So we have to extract our required or relevant information from this forecasted weather, and we have to translate it into its corresponding impacts. So that is the tricky part. So we should know about the impacts associated with each and every severe weather meteorological hazards. So there's those impacts we should have. So if you have that impacts, then according to corresponding hydrometeorological hazards, we can issue that impact to the targeted audience, so they can plan the mitigation strategies according to that. So we should ask some question to ourselves. So what are the impacts we are expecting from a hydrometeorological hazard? When it will occur? Where it will occur? What threshold is required from an hydrometeorological hazard for creating such an impact? And what is the quality of the data that we have used to analyze those impacts? So those things we should ask ourselves. So then after that, we should go for the impact assessments. So there are so many hydrometeorological hazards are there. So in this particular presentation, I am only concerning about the heavy rainfall. So as a hydrometeorological hazard, it will have some cascading hazards, primary impacts and secondary impacts, generalized impacts and cascading hazards are given here. Sometimes the secondary hazards are having more importance than the primary hazards, just like our health sector issues and all. So it's a generalized impact. So these impacts we should collect. So how we will collect? We can collect it from the historical data. Once we will have this historical data, then we have to see. So what is the threshold of that hydrometeorological hazard is creating such impact? So we should analyze the past events. We should analyze the past events. We should correlate each event with the impacts occurred that time. So we will come to know that hazard threshold from that study. We will come to know that, okay, such a particular threshold, crossing such particular thresholds will create such and such impacts. From such and such individual impacts, we can reach to an impact level for a particular event. So we will get a matrix from that past event analysis. That matrix will impact matrix. I will call it like impact matrix. That impact matrix will call the hazard thresholds against the level of impact. This level of impact we are calculating from the individual impact associated with each hydrometeorological hazards. So once we are having that impact matrix, then we will go to the risk matrix. Risk matrix is nothing but a color coded matrix, and this color will give okay actionable this thing. So what action we have to take, that we will get from that color coded message. So that matrix is nothing but it's a level of impact against the likelihood of impacts. Actually, most of the people might have seen this risk matrix. So it is actually a level of impact against the likelihood of impact. The likelihood of impact we can now consider as the likelihood of crossing that threshold value of that particular hydrometeorological hazard. So likelihood of hazard against the likelihood of the impact. So the bottom axis is giving the impact levels: minimal, minor, significant, and severe. And the left axis is giving its likelihood. So correspondingly, we will come to this color. So each color having its own meaning. It's already given. Green means actual business as usual. There is no warning is there. Yellow means be aware, be updated. This orange color means okay, be prepared, and red means take action. So it's the highest level of warning. So you see that in that impact bottom axis, if we are having from our previous, or we assessed that the level of impact we are expecting is severe, so it will be in the higher side, in the rightmost side. But the likelihood of that hazard is low or very low, then the color will never go to red. The color will be orange or yellow. If our likelihood, or we are expecting, if our confidence level is very high that it will cross that particular threshold, then the left axis will also go to the high, bottom axis already is at the high position, then only we will get the red colored message. So this is the generic description of different impacts. So how we have adopted this method for Kerala? Actually, in this particular presentation, I am showing for Thiruvananthapuram and Ernakulam districts. So as I said earlier, we have collected the impact data. MedCenter Thiruvananthapuram was having or the previous historical impact data with them. So from that 17 years impact data associated with the heavy rainfall is collected. Corresponding rainfall was also available at the MedCenter Thiruvananthapuram. That was also collected for these two districts. And then an impact category matrix was prepared based on the threshold method. It has been prepared, and risk matrix already I have shown. And then we have that impact matrix, which is a lookup table. Using that lookup table, we can assess, okay, if the coming rainfall is crossing this particular threshold, this kind of impact is going to occur. So the data collection was the Herculean task, because we were having data in MedCenter Thiruvananthapuram as disaster weather reports were available for sending this data to Pune for archives. This data was available at Thiruvananthapuram, but all the data was in hard copy. Apart from the recent data, all the data were in hard copy, and most of the old files were weeded out. It was in the storeroom. So we took all the things, all the data were then digitized. But this data was almost good. Actually, you can see the date, the event, what are the impacts occurred, and even in the remarks it has given the level of impact also. So this was a first level data. It was somewhat good data. So we have digitized it with the individual impact. From this individual impact, we have made an impact category. So we have that impact data. Then now we need a threshold. So here I told it is heavy rainfall is the hydrometeorological hazard. So we need a threshold which will create such an impact. So we took the daily rainfall data of that event day D. Okay, so the 24-hour rainfall which occurred on the event day for all the, this is for the Thiruvananthapuram I am showing here, for all the 5 stations we are having, and the district wise also, district wise average also it is taken. Apart from that, we have taken a 5-day cumulative rainfall prior to this event. This is because sometimes on a single day rainfall may not create issues. The previous day's rainfall will have its own influence on this impact. So in order to accommodate that, we have taken that cumulative rainfall prior to this impact also. So we have cumulative 5-day rainfall and a single day rainfall on that event day. In that cumulative day rainfall is then segregated into different bins. In that different bins, different impact levels will fall. Corresponding to each impact levels, we will have that single day rainfall here. So number of stations having less than 4 centimeter, 5 to 6 centimeter, like that we again categorize. So we are making a double threshold method here. So we are having a threshold corresponding to cumulative rainfall, and we are having a threshold corresponding to the single day rainfall. This single day rainfall threshold will somewhat take care of the spatial distribution.
Around 1 minute. 1 minute left.
Okay.
So quick.
Okay. So like that, we have created that impact matrix with the double threshold method. This is for Thiruvananthapuram. This is the impact matrix created for Ernakulam. And you can see that this Ernakulam case, it's the cumulative rainfall beams are bit in the higher side. So that means they need the Ernakulam district, not the city. I'm not talking about city. It's Ernakulam district as a whole. City case is different. So this is need more rainfall to activate. So if you are seeing this percentile analysis, we can see that the 99th percentile for all the 14 years, for the Thiruvananthapuram all the 4 months, you can see it is in the 6 to 7 centimeter only. 99 percentile, I am calling it as extreme. But in Ernakulam, it is 10 to 12 centimeters. So a 10 centimeter rainfall for Trivandrum during southwest monsoon is coming the extreme side, whereas in Ernakulam, it is the normal side. So its impact will be different. So we had this threshold, we have the impacts, we have the risk matrix, and different impacts were tabulated. Exposure data is not completely incorporated into this, but anyway, from the historical data, we have collected all the impacts and it is tabulated with the risk matrix. We can now issue the color-coded messages as IBF. So this is for Ernakulam, is also presented here. The data what we are having the impact and response matrix, but in order to give a pinpointed IBF, we should know more about the districts, so that the whatever impact level we have calculated is the higher side. Okay, it may not need that entire district will have the same impact. So the impact will vary in the entire district. So in order to know that, we should know its geophysical, physical, socio-economical, and vulnerability data. So we have to collect it. So we have collected that. Our meteorological, climatological data we are having, and other, this is for Thiruvananthapuram, we have collected this physical and socio-economic data. So everything, even the land use, land type, topography, all these things are very much needed. So flood susceptibility, landslide, all these things are collected, and we are thankful to Kerala State Disaster Management Authority for sharing the data. So using this data, now we are trying to make it more fine-tuned. Okay, which are the area it can happen that impact level will be higher. So here also for Trivandrum, if you see areas susceptible to landslide, you can see only 3 taluks are susceptible, other 3 taluks are not there. So the impacts we can give, we can more pinpoint that. So that is the thing we are now planning. So now already from 2020 onwards, we have started issuing this IBF for city level. 2021 we have started this for different districts. Okay, Kerala already now issuing for all the 14 districts. This is the stages of forecasting. Already respected DGM has mentioned it in the morning presentation. So in Kerala, they have issuing it to this disaster managers. Even in their website also it is available. You can check there. These are some of the bulletins they have issued. So this is the future plan. We need to automate all this.
Just quickly.
Yeah, last slide, sir. Last slide. So this is what we are now planning to do in this. Actually, the data we are having, model forecasted rainfall data we are having, realized data we are having, historical impact data, but it is not a big data. Whatever data now we are having is not a big data, but in the near future it will become big. Nowadays we are getting more and more data. So if we can ingest all these things to a machine learning algorithm, then it can decide, okay, which impact category it will fall, and we can fill it. We can give it into a GIS platform with the vulnerability and exposure data. Then we will get a dynamic IBF bulletin. So in this way, we are now planning and we are now moving towards that. Thank you.
Thank you, Arun, for the talk highlighting the impact need of the impact forecast, and IMD already working towards this. Thank you for your wonderful talk. Thank you. I think let up time we will go for next speaker. Okay. Thank you.
Thanks.
Yeah. So, Ranjit Kumar Paul is there?
Yeah. Yes, sir.
Yeah,
I'm here.
Please, yeah.
Please unshare the slide.
Arun.
Visible, sir?
Yeah, you have a lot of slides, so please be quick.
Okay, I'll be ending in time. No problem.
Yes, fine. No.
So should I start, sir? Is it visible?
Yeah, yeah. Please
Am I
go ahead.
audible
Yeah,
clearly?
yeah. Visibility.
Okay. Thank you. So the title of the talk is Modeling Subdivisional Rainfall in India using Deep Learning Technique. It's very much well known that agricultural performance of any country generally depends to a large extent on the quantum and distribution of the climatic variables, particularly the rainfall and the monsoon rainfall. Therefore, for proper planning and policy making, we need to have accurate modeling and forecasting of the important climatic variables, including the rainfall. And when we talk about the forecasting of the climatic variables, particularly rainfall or any other time series model, definitely the autoregressive integrated moving average model, which is the Box-Jenkins model, comes into mind, which has been a dominated time series analysis for the last several decades. But just like any of the parametric statistical technique, this technique is also based on some crucial assumption. And until and unless those assumptions are fulfilled by the data under consideration, we should not go ahead, because at the end of the day, we may be misled with the conclusion. So in that case, what happens in most of the practical situation, whenever we come across the data of the rainfall or any other climatic variables, we see that the linearity pattern does not hold. That means there is some kind of ups and downs, and there may be some non-linearity exists.
There is some problem in connectivity, I think. Hall B.
Sir, I think it's a internet connectivity problem of that person.
Yeah. So should we go to next speaker then?
Yeah, he's joining.
Yeah, please. Yeah, your connectivity issue. So please be quick little bit.
Now okay, sir?
Yeah, now it is okay, but bit quick.
Now I'll be quick. Yeah.
Man, just come to the conclusion and summary discussion part only. Discussion,
okay.
Introduction not required. Yeah.
Okay, no problem. So basically, the main theme of this particular paper is that instead of using the usual parametric technique, nowadays machine learning technique has come up very rapidly, and it has been established as a serious contender with the so-called parametric technique. And we have applied some machine learning technique along with the deep learning techniques and compared the efficiency of this technique along with the usual parametric technique like your ADIMA model. And this is the technique which we have used. I think it's nowadays well known to everyone. This is the deep learning technique, usual deep learning technique, that is long short-term memory, which has three variants we have used. One is simple LSTM, stacked LSTM, and the bidirectional LSTM. So, and the data set we have considered is the subdivisional rainfall data, monsoon rainfall data for the 30 subdivisions of India, and these are the different subdivisions we have considered along with these abbreviations. Before we go for the application of this technique, we had a look on the summary statistics, and just to have a look, we can see that the coastal Karnataka is having the highest average monsoon rainfall received, and followed by, of course, Kerala and Konkan and Goa subdivision. Of course, Assam and Meghalaya region also receives a quite good number, good amount of rainfall received. And the nice feature, the main thing which we can extract from this particular statistical table is that normality. So usual statistical model application is difficult as such on this particular data. Before we go for application of statistical model, we need to go for some kind of treatment on the data. So these are the simple linear trend, which is, I think, a very trivial thing. Just to have a look on the rainfall trend over the years in different subdivisions, we can see that in most of the subdivisions we had a very negative trend, and though very few we had a significant trend, negative or positive trend we observed. Now coming to the main part of this particular analysis is that we have compared this ARIMA model along with the three feature of these three type of LSTM model and the ANN and SDR. So obviously across all the subdivisions, we could observe that ARIMA model, which is a linear time series model, could not capture the pattern existed in the dataset, and it is the worst performer among all the competing models. Because of the pattern existed in the rainfall is quite non-linear and does not actually follow the linearity. So obviously ARIMA could not capture it. And the other technique like SDR, the LSTM, different variants, and ANL, they can be seen that they are better performer, though in this particular table we have only shown the RMSE and MAP. These are the two criterion, root mean square error and mean absolute percentage error. And we can see that around 10% the percentage error is coming for the base model, both the validation as well as the training part. So here we have bifurcated the data into 70 in 70 to 30 as training and the validation part. In almost all the subdivisions, we can see that the either machine learning technique or all the deep learning technique has come out to be the better performer in the model. And moreover, out of these 30 subdivisions, we can count that around 17 subdivisions, the deep learning technique, particularly the LSTM and bidirectional LSTM, has come out to be the better, followed by SBR. So the subdivision wise result we can just see like this, and all the 30 subdivisions. And coming to the conclusion, so we have used this 146 years data, Indian monsoon rainfall data for the 30 subdivisions, and we could empirically compare the forecast accuracy of the deep learning model along with the machine learning technique like artificial neural network and support vector regression, of course with the stochastic model like ARIMA. And we see that in terms of the mean error, mean absolute error, root mean square error, and mean absolute percentage error, the deep learning model has come out to be the better, followed by this expected, because it could not capture the nonlinearity existed in the data set. The content of this particular presentation has taken from a few of my recent papers, and these are listed here, and few of the R packages which have been prepared, they are also listed here. Thank you very much, and sorry for the inconvenience due to unstable internet connection from my side. Thank you.
Okay, thank you very much for your nice talk on this application. So since time is short, so we'll not take any questions. Okay, thank you. I think wonderful. So now we'll go to the next speaker. There is just Jayanti Pal is there. Dr.
Yes,
Jayanti Pal.
Yes,
Central. Yeah, please go ahead.
Okay.
Yeah, start the talk.
Okay, is my screen visible? Hello?
Yes, yes.
Visible, sir, visible.
Okay. A very good afternoon, all of you. I am Dr. Jayanti Pal, rightly working as an assistant professor in the Central University of Rajasthan. Today, my topic is about the changes in sea surface temperature, wind at 10-meter height, subsurface ocean temperature that is associated with the Indian Ocean dipole during the warming scenario. Now, the basic introduction, I think all of you know about this Indian Ocean dipole moment that manifests through the dipole pattern of the sea surface temperature. Here, the picture is actually depicting the positive phase of the Indian Ocean dipole. And if we see that in the climatology, I can see that if we calculate the climatology from the long-term mean, which is the average of almost more than 150, about 150 years, it depicts a climatology of like it shows that all the DMI value is at around negative. Whereas if we take the time average of 1980 to 2019, that shows the climatology which have every value is positive, and also it shows that it peaked at around September, October, November. So this Indian Ocean dipole event is actually identified first by the Saji et al. And Webster et al. They have identified this Indian Ocean dipole and measured through the dipole mode index, which is the sea surface, basically difference between the sea surface temperature gradient between the Western and the Eastern Indian Ocean. Now, in recent days, it is observed that the Indian Ocean dipole events are increasing positive in phase. So here, the picture that depicts the 10-year moving average and 30-year moving average, which clearly shows that at around 1950, the phases are continuously increasing in the positive direction. So along with that, in recent studies, several studies like Roxy et al. 2014-15, they have also mentioned about the warming over the Indian Ocean, specifically over the Western Indian Ocean. And here the picture is actually depicting the change in the equatorial region, change in the sea surface temperature anomaly over the equatorial region that is averaged over 10 degrees north and south, which clearly depicts a monotonous increase in the sea surface temperature anomaly from 1980. So from those things, actually, what is I frame that we need to study the what are the processes changing in the Indian Ocean over the Indian Ocean. So for that, we need to study the local ARC interactions. Now, to identify the local sea interaction process, here I identified the three primary variables: sea surface temperature, zonal wind at 10 meter from the sea surface temperature, and the subsurface or surface temperature as a primary variable. Further, I have taken the data SST for the head SST data, which is the mostly available at 1 degree resolution, and it is the most longest data. And wind at the 10 meter data is collected from the ERA5 data. Now here the data is collected from 1950 to 2019 because it is only available period from the ERA5. Ocean subsurface temperature has been also collected from the UK Met Office. There is a new subsurface data, EN4, which is now also available at 1 degree resolution from 1900, and it is in the monthly scale. So using this long-term data, I have framed a study so that I can study the interannual variation of the interannual variation of those parameters over the Indian Ocean, by considering the annual mean as well as the September-October mean. September-October I have taken because September-October-November is the peak phase of Indian Ocean dipole. So in the latter case, I have divided my total time temporal epochs into three parts. One is the available, whatever time period is available, that is a long-term period. And second, starting from 1950 and 1980. Now from 1950 I have taken because here we can see there is an increase during 1950, but it is not quite monotonous. But after 1980, there is a quite monotonous increase in sea surface temperature anomaly. So here first sea surface temperature, what we can see in the mean state and trend and standard deviation here, we see that over the eastern part of the Indian Ocean, the mean state of the Eastern Indian Ocean is increasing with the increasing like warming episodes, and also there clearly observe extension of the warm pool region, while the trend we can observe over the Western Indian Ocean, which is quite significant in the September, October, November. And if you see the standard deviation, interannual standard deviation, here also we can see, if we consider the long-term trend, the variability is higher over this region, whereas if we move to the warming episodes, the variability decreases. Now here I have analyzed the variation through UAF analysis, because normally we know that Indian Ocean dipole mode is represented by the second UAF of sea surface temperature of the Indian Ocean. So here you can see that the UAF and UAF2 of sea surface temperature, which considered the annual mean time cities, it shows quite interesting behavior during this time period, that when we consider the long-term average, the variability is maximum over the central Indian Ocean. Whereas if we shorten the time period, the variability is basically coinciding over the Eastern Indian Ocean, and also it looks like it was moving towards a eastern direction. The UF2 of the SON, that is September, October, November mean also depicts a dipole pattern. But when we consider the long-term mean, it shows a very strong tripole-like structure. And gradually it evolved as a dipole pattern. Whereas if we see the UF1 of SON, you can see that although we know that UF1 is mostly depicting the basin-wide warming, but during September, October, November, which is the peak month for Indian Ocean, the UF1 is actually depicting the dipole pattern of the dipole mode index. And also it shows the variability increases in recent decades. Now, the composite structure, also you can see that how the Western Indian Ocean, Indian Ocean is related with those modes, that is also analyzed through correlation analysis. Here we can see that the first component, that PC1, is well correlated with the Western Indian Ocean. So from here we can see that annual, the first UF of annual mean time series is depicting the variability of the Western Indian Ocean, whereas the first UF of September, October, November is actually depicting the variability of the dipole mode index. The composite analysis of positive Indian Ocean, because in recent decades, positive Indian Ocean is continuously increasing. So here we analyze the positive, the spatial structure of the positive Indian Ocean against the mean climatology. And here we see that with the increasing temperature, the spatial structure, the intensity of the spatial structure, specifically with the warm region, it is reduces. Now the zonal wind is at 10 meter height of the surface temperature. Here you can here see the mean zonal wind is actually not much changing, and the trend analysis shows that equatorial zonal wind is increasing continuously. The standard deviation also doesn't show much difference between the two epochs, because in case of wind, I have considered only two epochs, 1950 to 1950. One epoch is starting from the 1950 and a third epoch is starting from the 1980. The zonal variability actually doesn't change much, except in case of September, October, November, where we see that the UF1, the variability of the primary mode, is actually changing over during September, October, November. If we see the correlation study, so we can see that the PC1 again is well correlated with the Western Indian in Indian Ocean index, and PC1 during September, October, November of this zonal wind is well correlated with the dipole mode index. The composite analysis of the positive Indian Ocean dipole also depicts that the surface feature is actually weakened, because if you see the mean POD feature during 1950 to 2019, there is enhanced surface divergence that is observed, whereas in case of 1980 to 2019, there is weakening.
1 minute, please, 1 minute summarize.
Okay. The mean state of the subsurface ocean, to analyze the subsurface ocean, actually I have considered the two zones. One is the equatorial zone, that is termed as a 10 degree north to 10 degrees south. Another one is that 20 degrees south to 10 degrees south. So in both cases, it is observed that the September, October, November, and it shows the quite increasing trend. And also at the upper layer, the trend is almost 0.8 degrees centigrade for the ocean subsurface temperature. And the variability, interannual variability, also shows that with increasing temperature, the variability within the layer up from 50 to 150, this particular layer shows increasing variability for both zones. Now, if we now the variability study for first zone is actually shows that except the first component, other components are not much significant in September, October, November, because they only contribute at around 8% and 5%. Whereas during September, October, November, the UF1 is actually contributing more than 50% variance in recent decades. And this variation is actually increase in the warming episode. The second zone also depicting the same thing, where we can see that only the subsurface dipole is clearly observed, and in recent decade, with the increase in temperature, the mode changes its variability.
Please.
The composites. Yes, sir. I have only one slide now. And also from this composite analysis, it is observed that during when the September, October, November, it is observed that the subsurface dipole structure is actually trending with the increasing temperature. So from this preliminary analysis of the 3 parameters, it is observed that to understand the local Earth's interaction, the variability over the West, we need to understand the Western Indian Ocean variability. And also this Western Indian Ocean variability also affect the subsurface variability and the surface atmospheric science. But in recent decade with the warming phase, it is observed that the subsurface variability increases rather than the surface feature. These are the references. I would like to thank organizers for giving me this opportunity, and thank you. And this work is under the project of UGC BSR startup.
Yeah.
Thank you.
Thank you. Thank you, Dr. Jayanti, for highlighting the role of Indian Oceans. So this will be very interesting in future. Today also Dr. Rajivan sir was mentioning this. Thank you. So we'll go to the last speaker of this session, Dr. Nageshwar Rao. Okay. So please, we have to close by next 7-8 minutes. So you have 1 or 2 minutes less. Is it okay? Yeah. Because 4:45 we have to starting other session. Nageshwar, Murli.
Yeah, yes. Are you able to see my screen?
No, we can see your face only, not screen. Means PPT.
Screen.
Please share.
Let's share. Now?
Yeah. So be quick little bit, okay?
Yeah. Yeah. Sorry. Actually, my topic is predictability of extreme rainfall events over India during the southwest summer monsoon using NCEP GFS version 12 model in the present global warming weather. I am very much thankful to the Vijay and Yojan for their supporting to do this study. And it is well known that human-induced changes in the climate are not only increase the global average temperatures, but also increasing the frequency and intensity of the extreme weather and the climate events such as the heat wave, cold wave, droughts, floods, hurricanes, tornadoes, and thunderstorms over the various parts of the globe, noticeably more over some parts of the developed and developing countries. In the last 3 decades, temperatures are increasing abnormally, and since when we are compared with since 1950, it is higher than any preceding decade. And the changes, the increase in the temperature causes to increase the water vapor content, and it leads to the intensity frequency wise and intensity wise heavy precipitation events without any effect of the total rainfall amount various regions of the globe. It is particularly more for the South Asia. These extreme events are responsible for the floods and cause widespread destruction of the infrastructure and economic damage, loss of lives also. It is particularly more for the South Asia. According to the international disaster database, the economic loss of caused by the floods in India, it is almost 10%. It is $3 million per year. It is there. So in these recent decades, particularly the extreme rainfall events significantly increased over India. In most of the events, it is occurred during the monsoon, associated with the monsoon depression over the Bay of Bengal. So there is high demand to understanding and monitoring the prediction of the weather extreme events over India for the sustainability of the especially. So in the recent decades, there is a impressive development from the modeling, and it is significantly improved the prediction scale up to short time and the short and medium range forecast, particularly over the extratropical region. But it is the relatively low prediction for the tropical and monsoon regions. It is particularly low for the extended range forecasts in the tropics, one of the most challenging tasks to the meteorological community. Recently, in September 2020, NCEP has implemented the Global Ensemble Forecast System version 12 model and support to the stakeholders for the subseasonal forecast for the hydrological applications. This model forecast, it is available, reforecast data, it is consistent reforecast data, it is available for the recent 20 years, 2000 to 2019. This data, it is basically running the initialized with the 00 UTC once per a day. This up to 60 lead. Weekly once it is extended for up to 30 days every Saturday, every Wednesday with the 11 members. So I am using this model data to perform to see the performance evaluation of this model for in predicting the extreme rainfall events. And particularly this data, this model data is available day 1 to day 10. It is the 0.25, 0.5 resolution, and the later on day 10 to day 35 it is the 0.5. And up to day 10, they are stored the data every 3 hours accumulation. After day 10, it is a 6 hourly. And for that purpose, for uniformity purpose, I am making this entire data is the 0.2 by 0.25 by using the interpolation. And only I am taking for the everyday initial condition. That's why for consistency purpose, the entire data I am taking the only 5 members, 1 control and 4 attributions. And this data is for reference data. I have used Indian monsoon data estimation analysis. I have used from the NCMWF. It is well known that any model, direct model output, it is not useful. So it is needed to the statistical post-processing technique. In this method, I applied quantile mapping technique. And this method used to correct the model predictor rainfall distribution to the mapping into the observed rainfall distribution. This process is also called histogram equilibration or rank matching method. In this quantile mapping method, gamma probability distribution of the observed and forecasted values are used. The quantile mapping method is bias not calculated explicitly. And particularly, it is this method is the quantile mapping procedure is the transform between the 2 CDF, and this is the equation. The whole procedure is implemented here in the lay-one-out class validation way. These are my results. The first one is the IMDA analysis, and second row it is the raw model product, and the third one is the calibrated forecast. I didn't show all the leads. I have selected day 1, day 5, day 10, and day 15 for looking for. And what I observed, the model is able to represent the climatological pattern, JJS rainfall for all the lead times. It is where it is the prominent rainfall it is occurred, it shows those pockets, and where it is the low rainfall, it is those areas it is the low. But however, most of the prominent rainfall regions model have the large dry bias. Where is the low rainfall regions, it is there some wet bias it is there. After calibration by using the quantile mapping method, the wet bias it is decreased, low rainfall regions, and the dry bias also it is improved. The dry bias is decreased, and it is the rainfall it is improved those areas. You can see after calibration the patterns it is similar to the observation analysis data set. Even the pattern wise it is okay, but magnitude wise a lot of improvement it is there because of this method. And this is the bias already I explained, because low rainfall areas it is the large wet bias it is there, and prominent rainfall regions it is the dry bias it is there. After calibration it is almost 0 bias. And this is the mean difference. I have calculated what is the significance of the improvement in this method, and it is significantly improved. The bias is significantly decreased, either dry bias or wet bias. So this is the entry annual variability. Model have the large entry annual observation is the large entry annual variability in the compared to the model. Model have the day 1 it is up to some level it is able to pick up, but after that the entry annual variability is very less.
One minute. Okay. Please,
yes, sir. But after calibration, the patterns are improved, and entry annual variability also it is improved. And this is the CV. Even CV also only we can see that entry annual variability. Actually, the model have the large wet bias, and along with the lead time, the wet bias is increased. And but CV and IAV it is the less. But after calibration, it is improved for all the lead times. But the model have the day 1 forecast. It is good. Later on it is. Then this is the CDF plots. And here also model shows the less underestimation of the probability for the low frequency, low intensity rainfall events. That means most of the days it shows the wet days. In the model observation, it is not that much. Actually, at the same time, model is unable to predict the more than 100 mm, means 10 up to 10 centimeter it is able to predict. That is the maximum value. But after calibration, the prediction of the extreme rainfall events more than 10 centimeters also it is able to predict. This is the, you can see in the scatter plot also for all the time. You can see the range in the day one, it is okay up to 400 it is there. When it is observation, it is the 800. But other lead times, we increasing the lead time. With lead time, the range is decreasing. Most of the days, wet days, but the range, it is unable to predict the extreme rainfall events. But after applying, the lot of improvement it is there. Even correlation also it is decreasing for the short lead times, but longer lead times it is slightly decreasing.
Please summarize the thing. Okay.
Yeah.
I think
then I have taken the various categorical rainfall events also. Yeah. Then when we are looking for that the number of wet days, dry days, it is the significantly less in the model. After calibration, that is the improved, and wet days also significantly it is more. And particularly the wet days, particularly light rainfall events and moderate rainfall events is the over predicted in the model, and extreme rainfall is the underestimated. After calibration, the overestimation of the low to light rainfall to moderate rainfall it is the decreasing, and some of the extreme events are it is picked up and it is improved. And this is the pattern of here. You can see here before calibration, the number of wet days are more most of the part compared to the empty. The after calibration, the number of wet days significantly it is reduced.
Please conclude. I think this is okay. Yeah, now, you go to conclusion slide, please.
Yeah. It's significantly that improvement it is there for wet days and year events also. The number of wet days it is decreasing and extreme events are increasing. This is the box plot, same thing I have telling here. After calibration, the frequency bias is almost
go to the conclusion. Okay, I think this
this is the performance diagram. Yeah. This is the performance diagram. Okay, after calibration, it is particularly. Yeah, the model is GFS V2 model is able to represent the climatological features. But only thing is that number of wet days, it is the overestimation for the wet days and underestimation for the extreme rainfall events. But after implementing the quantum mapping method, the distribution of the various intensity rainfall events, it is well. The categorical skill scores also it is improved all the case. So the calibration method after applying these model products are very much useful. Particularly this forecast is mainly useful to strategic extended range forecast. It is very good, and it is the bridge like that medium range forecast and long range forecast, which is the taking the tactical decisions.
Okay.
Yeah.
I think thank you.
So these model products are in the present global warming era. It is highly useful to predict the extreme rainfall events after calibration.
Thank you. The main message we got it because after the calibration, it is able to do the extreme rainfall with more lead time. That is the message. Okay, that is good.
Yeah.
Good. Thank you. I think so. With this thing, we completed this thing. We thought initially one speaker is not there, but there, so that we just exceeded by 10 minutes. However, the session was good. All the 2 lead speakers, 1 invited speaker, and all the 6 contributory papers were presented on different papers. I think it was well cover all the topics. So Tyagi sir, final comments you would like to give?
Because of want of time, let me thank all the speakers, especially the lead speaker, invited speakers, and for keeping the timings and also presenting results. And also to Dr. Patnaik for managing the time pretty well. And to the organizers also for working out a very good program for this session. Thank you.
Thank you. Over to the local chapter. Thank you very much.
Thank you.
Thank you, Tyagi sir and Patnaik sir for chairing this session. Thank you, speakers and audience who have joined online and offline in this session. Today's program in Periyar Hall is completed. Remaining sections will be conducted in Hall 1 Pamba. As we are already late, the session of releasing the special postal covers have already started. So kindly log into that session in Hall 1 Pamba. Thank you.
Thank you, sir. Thank you.